All right, in this video, we're going to introduce our 3x3 systems of equations, which we're going to use a lot of the techniques that we looked at for 2x2 in terms of elementary row operations once we get into some examples. So with 2x2 systems of equations, typically we had, just an x and a y. With 3x3, we're going to take a step into the third dimension and have what we typically call the third dimension. We have x and y, and then now it's z. So similar to graphing the row equations in a 2x2 system, how each row of a 2x2 represents a line, each row in a 3x3 system represents a plane. So here we have the plane 2x minus 3y plus z equals 1, where the red part is indicated for higher values of z and cools off to the blue part, which is more negative values for z. So typically in three-dimensional plots, especially ones that involve color, your larger values of your third dimension, your higher values of z in this case, will be indicated by red, and then your lower values, your more negative values of z, are going to be indicated by blue. So you got think of like temperature almost, where red is a hotter temperature and it's higher up. Blue is typically a cooler temperature. It's associated with a cooler color, so it's lower. So here we have an x-axis, a y-axis, but then we have a height as well, which is the z-axis. So Desmos, unfortunately, is not good with 3D because it can't really do 3D. GeoGebra is really good with 3D. It really depends on whatever technology you're using. Even most computers, like Macs, have a grapher that can graph 3D graphs. So. However, the issue is, even though we live in a three-dimensional world, 3D graphs take some time getting used to. The better you are with them, the easier things to model in 3 dimensions will be. For instance, many video games, at least the ones now, are 3-dimensional based. So when I was younger, it was like 2-dimensional. You had length and width, but now you have a lot of depth to the games as well. So recall from geometry class that if we're going to look at the rows and the intersection of the planes, the intersection of two planes is a line. So for instance, if you look at two walls meeting, the corner, that part that they meet it can be represented by a line. And then if we take a line and intersect it with a plane, like a point going through, like a pencil going through a piece of paper, that is a point. And so a solution to a 3x3 system of equation is a 3-dimensional point that has an x-coordinate, a y-coordinate, and a z-coordinate. We could also have parallel planes which will not intersect. So if we take a piece of paper and lay it down on the table, and then we hold another piece of paper above it so it's not going to intersect at all, those would be parallel planes. And just like in the 2x2 systems of equations, those don't have an intersection, which means there's no solution. So again, the good news is everything we talked about for a 2x2 system of equations, even the vector interpretation, it also applies for a 3x3. So if you're really good at 3x3 and 3-dimensional vectors, it's the exact same concept, just bumped up a dimension. We are going to look at the row operations that we talked about in the last section, where we can switch 2 rows, multiply a row by a non-zero number, and then add or subtract 2 rows as well. So that's what we're going to look at when we get into some examples in this section, which will be in the next video. And if we had more time and training on them, we could probably do a lot better in using that technique with 3-dimensional equations. But we can always work with the rows of a matrix and find our solution using the inverse matrix. But we are going to focus on the 3 types of elementary row operations. We can interchange 2 rows, we can multiply a row by a non-zero number, and then we can do that and add or subtract 2 rows as well. So just like it was for the 2x2s. So our goal in this section is going to make a system of equation with a matrix form such as this one, where we have like 2x minus 3y plus 1 equals 1, negative x plus 4y minus 5z equals negative 8, and negative 3x plus y plus 2z equals 0 into our identity matrix where we have ones along each of the main diagonals, first row, first column, second row, second column, third row, third column, and then zeros elsewhere. Once we have it in this form, then whatever's over here is going to be X's solution in the first row, Y's solution in the second row, and Z's solution in the third row. And we'll take a look. We'll start our first example in the next video. So I will see you